I hope you're ready for some integration using polar coordinates, because in this video I have an example where we have to convert from Cartesian to polar coordinates and then we need to evaluate. So as usual, I suggest you pause the video, try and solve the problem yourself, then come back and see how I solve it. Okay, so when converting double integrals from Cartesian coordinates to polar coordinates, there are three things you need to worry about: the differential area, the function we are integrating or the integrand, and the region of integration. Okay, so let's start with the differential area. How do you convert this from Cartesian to polar? We know that in Cartesian, dA could be equal to dx dy, or dA could be equal to dy dx. In polar, the differential area is equal to r dr d theta. Okay, what about the integrand or the function we are integrating? So in Cartesian, if we have x in polar, it's r cosine theta. If we have y, it becomes r sine theta. If we have x squared plus y squared, we have r squared. Okay, what about the region of integration? The only way you can figure this out is by sketching the region. So let me write here from the sketch. No matter how smart you think you are, please sketch the region. And also please don't do this mistake. I see this quite often. I see people trying to convert, well, y, this becomes r sine theta, and this becomes square root of 2 minus r sine theta all squared. That is completely wrong. Please don't do this. Otherwise I'll be very sad. So let me erase this. Alright, so now let's see how can we proceed. Now let's sketch the region of integration. So if you look here, we have dx dy, which means we are integrating with respect to x first. So we look at the inner integral and we see the lower limit y and the upper limit square root of 2 minus y squared. I'm just gonna write x equals to y here and x equals to the square root of this, since we are integrating with respect to x first. And then we integrate with respect to y. This means that the lower limit here is y equals to 0 and the upper limit is y equal to 1. Okay, so now let's sketch the region. So this is the x-axis, this is the y-axis. Okay, so now let's sketch the lower limit x equals to y. This is just a straight line with slope equals to 1. So let me write this. This is x equals to y. So we're done with this. Now let's take a look at this. This here looks like an equation of a semicircle. If you can't tell right away that this is a semicircle, you can square both sides. So you get x squared equals to 2 minus y squared, and then if you take the y squared on the other side, you get x squared plus y squared equals 2. So this is an equation of a circle, and if you're taking the square root, it becomes a semicircle. Okay, so which part of the semicircle are we interested in? Let me first sketch the entire circle with a radius square root 2. So this is square root 2, square root 2. So we have x equals to the square root of something, and the result of this square root has to be either 0 or a positive number. You can never get a negative number out of the square root. So this means we're looking for the semicircle where x is either 0 or bigger than 0. This means we're looking for this semicircle over here, and you can ignore the rest of the circle. So let me sketch this here. Good enough. Okay, so this is root 2, this is root 2, this is negative root 2. And we see the semicircle and the line intersect at this point. And it will be a good idea if we figure out the y coordinate of this point. how can we do this? So this point is the intersection between two functions, x equals to y and x equals to the square root of 2 minus y squared. So if we want to figure out this point right here, we're going to do the simultaneous equations. We have x equals y and x equals to the square root of 2 minus y squared. I'm going to substitute x with y, so I have y is equal to the square root of 2 minus y squared. I'm going to square both sides. I get y squared is equal to 2 minus y squared. I get 2y squared is equal to 2. Therefore, y is equal to positive or negative 1. Of course, here is y is equal to 1. Y equal to negative 1 will be on the other side here. Okay, so now let's sketch the y limits. We have y equals to 0, which is just the x-axis. So this is y equals to 0. And we have y is equal to 1, which is going to be right here. So now we have all our limits. Our region has to lie between these two lines. So it's either this region or that one. How could we tell? Well, we look again, we have dx dy, which means we're integrating with respect to x first, then with respect to y. So if we sketch arrows going in the horizontal direction, and again we're using the horizontal direction first because we have dx, the lower limit should be x equals to y, and the upper limit is the square root of 2 minus y squared, which means that we should always enter the region through this curve, and we should always exit the region through this curve. So if I sketch arrows going in the horizontal direction, I see this is the region here where we always enter at the line x equals y, and we always exit the region through the part of the semicircle. So this here is our region of integration. Okay, so now we have our region of integration, and we've already figured out how to convert the differential area and the function. So now we can set up the double integral and integrate. Before we do this, let me resketch the region. So the y-axis, the x-axis, and the region looked like this. Remember, this line was x is equal to y. Okay, so now let's set up the double integral. The function was x, and if we convert this, it will be r cosine theta. And since we're using polar, we have to add the Jacobian r. Then we have dr d theta. Then we need to figure out the limits of integration. Again, since we're using polar, we have to start at the origin and go radially outwards. And you see, we always enter the region through the origin, and we always exit the region through this part of the circle. So the lowest value r could take is 0. The highest value r could take is the radius of this circle, which is equal to root 2. Now we need to figure out the limits of theta. So to figure out the limits of theta in polar coordinates, we go to the positive x-axis and go counterclockwise. So when theta is equal to 0, which is the positive x-axis, the region is defined. And the region is defined until we reach this line over here, which is x equals to y. So this line here has a slope of 1. If we have a 90-degree angle, this has to be 45 degrees. So 45 degrees is equal to pi over 4. Which means the lowest value theta could take is 0, the highest value theta could take is pi over 4. And now we can evaluate. So, can I rewrite it? We have r squared cosine theta dr d theta 0 to root 2, 0 to pi over 4. So if we integrate this, the inner integral, we have r cubed divided by 3. Cosine theta, and we evaluate this from 0 to root 2, and we get root 2 to the power of 3 divided by 3 cosine theta minus 0. So now we have the integral from 0 to pi over 4 root 2 to the power of 3 divided by 3 cosine theta d theta. So this is just a constant, and if we integrate cosine theta with respect to theta, we get sine theta. And we have root 2 to the power of 3 divided by 3, and evaluate this at theta equals to 0 and at theta is equal to pi over 4. So if we take this as a common factor, sine pi over 4 is root 2 over 2 minus sine 0, which is equal to 0. So if we simplify this, you get root 2 to the power of 3 divided by 3 multiplied by root 2 over 2. So if you simplify this even more, you get 2 root 2 divided by 3 multiplied by root 2 divided by 2. This 2 cancels, and root 2 times root 2 is equal to 2. 3 times 1 is equal to 3, and this is the final answer. I hope this was helpful. If you have any questions, please leave them down in the comment section below, and I'll be more than happy to answer them.